The bonds in covalent bond could be either polar or non-polar. In a polar covalent bond, the bonding electrons are shared equally between the atoms, while the bonding electrons in polar covalent bond are shared unequally. The bonding electrons in polar covalent bond are closer to a more electronegative atom. Electronegativity is the ability of atom to attract the bond pair toward itself. Means in a covalent bond, the bonding electron is closer to a more electronegative atom than the lesser, resulting in partial charge of the atom. Delta plus for the less electronegative atom. Since the electron is closer to a more electronegative atom, it will have a delta negative charge. These charges result in dipole, which is represented by arrow from less to a more electronegative atom. The trend in electronegativity in periodic table is increased across the period and decreased down the group. It means that elements on the top right of the periodic table has higher tendency to be a delta negative charge atom in a covalent bond. Molecule with non-polar covalent bond will be a non-polar molecule. However, molecule with polar bonds with the right shape could be a polar molecule. Polar molecules are molecules with a net dipole moment, which can be determined through the net vector from the shape of the molecule. Take this kit as an example of a molecule. At each limb, she has similar surrounding atom and a central atom at her belly. Look at how the atoms are connected in the covalent bond. Imagine this as the shape of the molecule. Imagine the surrounding atom is more electronegative than the central atom. Hence, the dipole moment will be from the central atom to each of the surrounding atoms. Then, there will be an outward force and downward force acting on her. Since the surrounding atoms all has the same electronegativity, the strength of the outward force is equivalent to the strength of the downward force. The upward and downward forces cancel each other, which make her to have a no net dipole moment. Hence, it is a non-polar molecule. Take this kit as a molecule in another example. Each limb has surrounding atom, but one of the limbs has different atom with higher electronegativity than the other surrounding atom. There is still outward and downward force acting on the molecule, but the outward force is stronger than that of the downward force, which result in a net dipole moment to the top, and hence this molecule is a polar molecule. Let's go into real molecule. Take water, which is bent in shape. Oxygen is more electronegative than hydrogen, which causes a dipole from hydrogen to oxygen. As a result of this dipole, there is a net dipole moment to the top towards oxygen, which makes water as a polar molecule. Another example is carbon dioxide. They are linear in shape, and oxygen is more electronegative than carbon. Even though the C double bond O is a polar bond, but the dipole cancel each other. There is no net dipole moment in carbon dioxide, making it a non-polar molecule. Covalent bonded molecule has intermolecular forces between them. These forces are weaker than the covalent bond, and it will determine the physical properties of the molecule. There are three types of IMF, which is permanent dipole-dipole forces, London dispersion forces, and hydrogen bonding. Permanent dipole-dipole forces is a forces between polar molecule where the permanent dipole in the polar molecule attracts one another. Definitely, the delta positive of one molecule is attracted to the delta negative of another molecule. Since polar molecule has a permanent charge, its liquid can be deflected when placed near a charged rod. London dispersion force is the weakest IMF, and it is the main force between non-polar molecules. It happens when at an instant a non-polar molecule created a temporary dipole which caused the electron in the neighboring molecule to repel and hence created induced dipole. The attraction between this temporary and induced dipole is the London dispersion force. This force is a force when non-polar gases such as hydrogen gas is compressed to be a liquid. The London dispersion force is affected by two factors, which are the number of electrons and the number of contact points. As the number of electrons increases, the London dispersion force becomes stronger, which explains why iodine appears as a solid at room temperature, while bromine is liquid and chlorine is a gas at similar conditions. Other than that, straight-chain molecule will have a stronger London dispersion force as more contact points for the London dispersion force to form compared to a branch molecule. Hydrogen bonding is a special IMF between a molecule with hydrogen connected to either F, O, or N, and lone pair of either fluorine, oxygen, or nitrogen from another molecule. It is the strongest IMF, hence it is termed as bonding. This is the force exclusively for three most electronegative atoms, which is fluorine, oxygen, and nitrogen, F, O, N. Water can form two hydrogen bonds per molecule as oxygen has two lone pairs. IMF affect the physical properties of the molecule, which include viscosity, surface tension, boiling point, and solubility. Viscosity is the resistance of liquid to flow. The higher the viscosity, the harder for the liquid to flow. Stronger IMF will cause molecule to have higher viscosity. In this example, as the number of carbon in the organic molecule increases, the London dispersion force becomes stronger and hence the viscosity becomes higher. Surface tension is the energy needed to overcome the inward attraction force of the surface molecule in the liquid. The stronger the IMF, the higher the energy to break this attraction, hence higher surface tension. Look, this perfect shot of surface tension of water right before the swimmer breaks it. It can be expected that molecules with stronger IMF will have a higher BP. In this example, two of these molecules, HCl and H2S, are connected by permanent dipole-dipole, while fluorine and argon are connected by London dispersion force. Polar molecule with permanent dipole-dipole definitely will have a higher boiling point than non-polar molecule with only London dispersion force. H2S has higher boiling point than HCl because H2S is more polar, hence stronger permanent dipole-dipole. Straight chain molecule will have a higher boiling point than branch molecule of the same number of carbon due to a stronger London dispersion force as the contact point is higher. HF has exceptionally high boiling point compared to other hydrogen halide because it is connected by hydrogen bonding, while the others are connected by permanent dipole-dipole. Molecules with the same IMF are soluble in one another. Since hexane has London dispersion force, while water is hydrogen bonding, they are immiscible in one another. While both iodine and hexane are connected by London dispersion force, hence the London dispersion force extended when they are mixed together. Alcohol are able to be miscible in water, as the OH group in alcohol can form hydrogen bonding with water molecule. But the solubility of alcohol decreases as the non-polar carbon chain increases.